For decades, the idea of temporal anomalies, bending the fabric of time to our will, has totally captivated us. But what if I told you the boundaries of time are actually way more flexible than we ever realized?
Seriously, do you already have a time machine in your pocket? It's a real question. Take a second to challenge your assumptions about time travel. You're probably picturing a glowing, spinning DeLorean, right? Or maybe some massive metallic ring. But the truth is, the smartphone sitting right there in your pocket relies on actual, mathematically sound time travel every single day. Without applied temporal mechanics, those navigation apps you use to find the nearest coffee shop, completely useless.
To understand why, we have to look back at Albert Einstein's brilliant revelation. See, time isn't an absolute, steady ticking clock that just governs the universe uniformly. Instead, time is a flexible canvas. It's completely localized. We call this phenomenon time dilation. Basically, the flow of proper time, meaning the time measured by a clock you're holding right now, literally changes depending on how fast you're moving or how deep you are within a gravitational well.
Okay, so let's dive into this, because this distinction really sets up our entire journey today. We need to draw a hard line between two radically different concepts. On one hand, we have forward time travel, which is governed by relativistic time dilation. This is a tested, everyday engineering reality. On the other hand, we have backward time travel that relies on extreme geometric deformations called closed time-like curves, and it remains a paradoxical, boundary-pushing, mathematical impossibility. Think of it like a video player. Forward time travel is just hitting fast forward, which is a proven reality. Backward time travel is hitting rewind, which in this case requires breaking the player itself.
Part 1, forward time travel is real. Let's start with what we know actually works. We're going to ground ourselves in the mechanics of the Navstar Global Positioning System, or as we all know it, GPS.
So, the GPS network consists of satellites orbiting a staggering 20,000 kilometers above the Earth, and they're just ripping through space at 14,000 kilometers per hour. Because of these extreme altitudes and incredibly high orbital speeds, the highly precise atomic clocks on these satellites experience proper time completely differently than we do down here on the ground. They are literally traveling through time at a different rate.
Let's break down the opposing forces acting on those clocks. First, special relativity dictates that because the satellites are moving so incredibly fast, their clocks actually tick slower, losing about 7 microseconds a day. But general relativity comes in and says that because they are further from Earth's gravitational pull, they tick faster, gaining 45 microseconds a day. The result of this? A net daily drift of exactly positive 38 microseconds.
Now, 38 microseconds might sound absolutely tiny, but the real-world stakes here are massive. If engineers didn't pre-adjust these clocks before launch, and if your phone's microcomputer didn't continuously calculate this temporal shift, well, your GPS navigational fixes would drift by a staggering 10 kilometers a day. The entire global network would become totally useless within just 2 minutes. So yeah, forward time travel isn't fiction. It is a concrete, strictly managed component of modern space navigation. Which brings us to part 2, the backward time travel problem. So, what happens when we try to put the universe in reverse? This is where we leave the safe harbor of engineering reality and venture into the mind-bending, exotic physics of the past. Backward time travel requires something called a closed time-like curve, or CTC for short. I want you to imagine a massive curvature of space-time that tips the light cones of relativity all the way over. It's kind of like a record skipping backward to play the exact same note again. It essentially forces a trajectory to loop back and intersect its own global past. You aren't just moving to a different place, you are returning to your exact starting point in both space and time.
But returning to the past obviously creates logical paradoxes, like, preventing yourself from entering the time machine in the first place. Theoretical physicists like Igor Novikov proposed the self-consistency principle to try and solve this. Imagine firing a billiard ball into a time-traveling wormhole. Instead of hitting its younger self head-on and stopping the timeline, the universe's math dictates it can only deliver a glancing blow. It alters the younger ball's trajectory by the exact, precise amount needed to send it into the wormhole to deliver that very same blow. Basically, the timeline mathematically enforces its own consistency.
Still, most physicists just don't buy that local paradoxes can simply be smoothed out like that. The great Stephen Hawking proposed the chronology protection conjecture. He argued that the instant a time loop begins to form, quantum vacuum fluctuations would build up exponentially at the boundary, creating an infinite energy feedback loop. Meaning, the universe would literally destroy the time machine the exact microsecond it was turned on, keeping the cosmos, as he put it, entirely safe for historians. The universe, it seems, has a built-in anti-tampering mechanism.
Moving on to Part 3, the warp drive energy crisis. let's see how our time travel problem builds into the ultimate sci-fi frontier, faster than light travel. Surprisingly, this shares some incredibly deep mathematical DNA with our backward time travel problem.
Back in 1994, physicist Miguel Alcubierre created a mathematical model proving warp drives were actually possible under general relativity. Instead of accelerating the ship, which breaks the speed of light, his metric contracts the space in front of the ship and expands the space behind it. The ship itself sits totally motionless inside a flat warp bubble, experiencing zero local acceleration. Sounds amazing, right? But there's a fatal flaw. Unlike our GPS satellites that just need solar panels, this drive requires exotic matter, specifically an absolutely impossible amount of negative energy.
Just how much negative energy? Well, early calculations show that to create an Alcubierre warp bubble just 100 meters across, you'd need an amount of negative energy equivalent to 10 to the 90th power kilograms. To put that into perspective, that is literally greater than the mass of every single star and galaxy in the observable universe combined. It's a completely insurmountable figure under our current understanding of physics.
And here's the kicker. Even if we somehow found a universe's worth of negative energy, the physics still won't let us survive the trip. Quantum field calculations reveal that the front of the warp bubble acts just like the event horizon of a black hole. The moment you activate it, it emits infinite Hawking radiation. That radiation would instantly incinerate the ship and absolutely anyone inside it. So the 1994 Alcubierre model, while a total mathematical triumph, is a physical dead end. That leads us to part 4, new models and resonant cavities. Theoretical physics never stops evolving, you know? To understand where we're going, we have to look past the impossible requirements of the 90s and gaze right into the near future. Right now, as we speak, scientists are actively rewriting the math to bypass these fatal flaws. We're finally moving away from that 1994 Alcubierre metric with its impossible negative energy and instant incineration problem, and we're moving toward cutting-edge theoretical frameworks like Chance M. Glimm's proposed 2026 resonant cavity model. The goal here is monumental: mathematically generating a warp field using only positive, normal energy that actually exists right here in our universe.
And this brilliantly illustrates how the problem is being tackled today. Glenn's model modifies the geometric shaping function using complex mathematical values. By doing this, the energy density requirement literally flips from negative to positive. It replaces the need for exotic matter with intense electromagnetic resonance occurring within a specific type of material called a lossy dielectric. Basically, that's a material that absorbs and dissipates electromagnetic energy. It's a theoretical way to achieve localized space-time distortion without breaking the fundamental laws of thermodynamics. A real game changer.
So, from the very real-time dilation being corrected right now in your GPS apps, to the tantalizing positive energy mathematics of tomorrow's warp drives, the boundary between science fiction and science fact is way thinner than it appears. We just need the unified theory of quantum gravity to read the final rules of the universe. So I'll leave you with this to think about. Once we finally bridge that gap between Einstein's relativity and the quantum world, what other impossible sci-fi concepts will cross the line to become our new reality? Thanks for joining me on this explainer. Keep wondering and keep looking up.